Hey guys, today we're going to do the force cart lab, and the idea is we're going to look at the relationship between the net force on a system and the acceleration of the system. Our setup is fairly simple. We're going to have a track with a cart on it. Attached to the cart will be a string that is also attached to a pan over here. This pan initially has a mass of 50 grams. We have additional masses on this cart that we can move from the cart to the pan, okay? There will be a motion sensor set up back here. So there will be a motion sensor that will allow us to determine the acceleration of the cart. So we have a cart and the pan and a track. So this is sort of our setup of what we're going to be doing. And our goal is to figure out the relationship between the acceleration of the cart pan system and the net force on that system. I want you right now to think about the forces on the cart and the forces on the pan and draw a quick free body diagram of that. You can pause it. If we consider the cart, the pan, and the string connecting them all one system, so now all of this is in my system, then the force of tension becomes an internal force. And we don't have to worry about it. The force of gravity, well, we have two forces of gravity. Are they the same here? No, this is the force of gravity of the cart, this is the force of gravity of the pan, and we should keep those separate. They're not the same number. But the force of gravity of the cart and the force normal of the cart against the track, those two will cancel each other out. They're going to be one positive, one negative of equal amount. Otherwise, the cart will fly up off the track or go down through the track. And so the net force on this system, because those two are internal and those two cancel each other out, is just the force of gravity of the pan. The force of gravity of the pan becomes the net force on our system, and in this case, it's going to be our independent variable. It's the thing we're changing in our experiment. We will compare that to the acceleration of the system. The pan and cart have to have the same acceleration because they're connected by the string. I'm going to ask you to come up with the meaning of the slope. Okay, so we're ready for the first run on our data. Our pan has 50 grams on it. Let's go ahead and measure the acceleration, which we're going to get from the acceleration versus time graph. We'll just have to see where the line shows up. We're ready to go ahead and collect data. All right, so it was during this time period right here, and if I hover there, I find our acceleration is around 0.7. 0.7. I feel we're only accurate to about 1 sig fig here. It's 0.73 right where it's at, but it does bounce up and down quite a bit. And so we're just going to go with 0.7 for the pan of 50 grams. Let's go ahead. I'm going to move 10 grams. 10 grams from the cart to the pan. So now my pan has a mass of 60 grams. So going up to 60 grams, we're going to collect data again. Okay, this time we are at about 0.9 with 60 grams. Now we have 70 grams on the pan with 70 grams. We get a acceleration of 1.0. Here we are with 80 grams. All right, here we have 1.2 1.2 meters per second squared is the acceleration with 80 grams on the pan. All right, now with 90 grams on the pan. All right, here we have acceleration is 1.4. Call that 1.5. 1.5 with 100 grams on the pan.